This is lecture 9C on an example of a separable equation. Okay, here's our first example. We're going to start with this differential equation, dy by dx equals 4y. This is separable and can be written in the form that we want. I'm going to write this form a million times. Some function of y multiplying dy by dx equals a function only of x. Alright, I'm going to divide by y, assuming y is not constant, and my n of y is 1 over x. Here's my dy by dx, and after the equal sign is a function only of x, which is 4, and the constant is okay in this case, as long as it's not a function of y. Right. Now we can integrate both sides. Sorry for the squiggly green line, I don't know how to get rid of it. So I'm going to write this as 1 over y dy equals 4, function of time, not y. So this can be a t, and this is a function of time. Right. Now I'm going to integrate both sides. When you integrate 1 over y, you get the natural log of y plus c1 because it's an indefinite integral. When I integrate 4, I get 4 times t plus c2. Alright, this brings us to actually, theoretically, there is a constant of integration on either side of the equal sign, but because these two numbers are constant, it doesn't matter that we solve for them separately. We can lump them together, and this is how it's typically done. We lump them together on the right-hand side. So on this side, we just have the natural log of y. Because it's constant, c1 has gone over to the other side, and we don't write it as c2 minus c1. We just give it the value, we just call it c. Here's 4t. Alright. I hope you saw what I did there. I wrote the function as I put all of the y terms over here with dy by dx. On the other side of the equal signs, I put all of the m terms. I can separate this out. I've got n of y times dy equals m of x, or m of t times dt. Then I integrate both sides. When I integrate these sides, I get two constants of integration, but we lump them all together on the left-hand side and call them c. We don't need to solve for two constants and then combine them. We can just solve for one constant at a time. At this point, we're done with the calculus. So now that we're done with calculus, we have to use some algebra to isolate for y. We want to find y of t. So to do that, a very common thing to do is exponentiation. Remember what our solution looked like before? Let me get the pen. The solution was natural log of y equals 4t plus some constant c. And I really want y by itself, not in the natural log of y. So to do that, I exponentiate both sides. So I've got e to the natural log of y gives me the y. Here I have e to the 4t plus c. This can be broken out as e to the 4t times e to the c. Now, again, we simplify the constants. We don't need to find the e raised to some constant. This is just a constant in itself, so we abbreviate this whole thing as just c. And this is what we get. Y equals some constant c, e to the 4t. This is the general solution. It denotes a family of curves, one for each value of c. But we can find for c, a value for c, if we have one data point. That is, if we know y at some value of t. A very common one is the initial value. Remember, I talked about initial value problems. If I know y when t equals 0, I'm going to call that y0. I'll substitute that into the equation. So here I have y equals c e to the 4t. And this is, let me get rid of that. I want to write it like this. Y, which is a function of time, equals some constant c e to the 4t. Right. I know the value of y at 0. I'm going to call this y sub 0. Substituting 0 into this equation gets c e to the 4 times 0. Well, e to the 0 is 1, so we end up with y0, the initial value, is the value of the constant. I can substitute that into my general expression right here. Y is a function of time, time equals y0 e to the 4t. And that's the solution of that differential equation. So part of it, we use calculus. Once we set the problem up right, and then we used algebra. Let's go over the tricks that we used. Okay, one of them was the use of exponentiation as the inverse of logarithms. That's very commonly used. Another is the constants of integration are combined and simplified, and we write them. It's customary to write all the constants as one value over on the right hand side of the equation, and if we have any nonlinear function of those equations, of those constants, we just replace that with another constant. And that's what it's we're talking about in 3. When the constant of integration appears, for example, as the argument of transcendental, say, e to the c, there's no reason to calculate the exponent of a constant. That would also be a constant. We just replace the whole thing with c.